So Monday, the plan is we're going to go over the practice test, and any questions you have over chapter 3, 4, 5.1, 5.2 material, let's get that knocked out Monday. And then Wednesday is your test, and you'll take it during class like what you did the previous test. All right. Any questions on that? So study good over the weekend. If you haven't, or if you have some of the homework problems you haven't done yet, I'd highly recommend doing them. With that and the practice test and the quiz you took, you should be pretty good on the actual test. And remember, you can use your notes, and you can use what else? Your textbook, calculator, all of that kind of stuff. And also, if there's any of you that are doing the online calculators, let's see if I go down under modules. If you're doing these online calculators, you know, if you have trouble with it, email me over the weekend so that we could get that knocked out. Okay, we can meet via Zoom. As far as I think the mean, median, and mode and standard deviation stuff, and the combinations and permutations, the probability related stuff. I think I've already told you the calculators that's under, but I can't remember it off the top of my head. But it should be easy enough for you to find. But again, feel free, you guys that are using that, you're not using a graphing calculator, feel free to email me and we'll set up a Zoom session over the weekend. Any questions on that? I'm not Zooming on the weekend. All right, you said that. Anyway, I'll close that. So you click on modules, you go to this thing called online stat book and click on it, and you'll see all of this stuff pop up. Now, I opted not to do the chapters 1, 2, 3, or 4, and they don't have material that's good on chapter 5, so I did not make a link to that. So chapter 6, what we're going to look at next, that's what we'll do. Now this took a while because I have such a horrible Wi-Fi connection down to, it's like halfway working today. So I noticed that if I click on it, it takes a long time for it to pop up. But anyway, click on this chapter 6 docx. And now I'm going to stop share and go to the screen that you would go to if you were to do that. And I'm going to close this particular page just because I need the Wi-Fi juice. All right. So you click on that chapter 6 links and you'll come to this page right here. It only has 3 things here, but we're actually going to look at a couple of other videos that I neglected to load. But to get to the site, just click on where it says video. By the way, you see it says standard. That's like a written lesson, like notes, like what I give you. And you're welcome for any of these areas that we're going to be covering to get on this site, online statistics. And if you want to look at their notes because you think it might help, I'll leave that up to you. But we're going to click on video. And it's going to go to a video that I don't want because I forgot to put the links on for the videos that I do want. And eventually it's going to get there. All right. So I'm going to go on and close my Canvas tab, again, because of Wi-Fi problems. And then let me just stop share and make sure that I am sharing the right screen because sometimes that messes up. So you see something that says normal distributions, right? What we're going to go up to is the introduction video. So under item number 2, introduction, I'm going to click video, and it'll go to the second video, which is what we want. So we're going to watch the second and third video, just so you know. And again, this is going to be a short class. After we watch the videos, I'm going to pull up the appendix section that's in your book and on the cards that some of you might have, the formula cards, because I want to talk a little bit about where you find information about normal distributions on that. And we'll get into that heavier starting next Friday. You know, you'll take your test Wednesday, then Friday we'll get into chapter 6. Monday we'll review, all right? So here we go. That is a very good question. Hold on a second. Chat back to me the answer to this. Are you talking about a graphing calculator? All right, that is a very good question, and I'm glad we're recording this. The Student Success Center, the SSC, has 2 sets of graphing calculators that they loan to students. And my understanding is they wipe them down between students because of all the COVID stuff, right? So the idea is you go in there and you give them a photo ID, and then they let you check it out. I think they do like 2 hours. So that gives you time, well, especially for our class, it's only an hour long. But yeah, go in there and you can actually, in the SSC, check out a graphing calculator and mess around with it, learn how to do it. And remember, I've gone over in class how to do it, and also there's videos. If you look under modules, you'll see the TI-84 tab, and you click on that, and you just look up the topic on it. Whichever topic it is that we're covering that you want to study for it. Hopefully that answers your question. But yes, by all means, take advantage of those SSC calculators, you guys. All right, anybody else have a question? Okay. You are very welcome. Thanks for asking. That was a great question to ask. There might have been some other people that need that as well. All right, anybody else any questions before I start the video? All righty. I forgot the popcorn. Anyway, never mind. Here we go.
The normal distribution is the most important and widely used distribution in statistics. You've probably already heard of it, and you'll hear much more about it here and in later chapters. The normal distribution is sometimes called the bell curve, although the tonal qualities of such a bell would be less than pleasing. The normal distribution is also called the Gaussian curve, after the mathematician Carl Friedrich Gauss. As you'll see in the section on the history of the normal distribution, although Gauss played an important role in its history, de Moivre was the first to discover the normal distribution. Strictly speaking, it is not correct to talk about the normal distribution, since there are many normal distributions. Normal distributions can differ in their means and in their standard deviations. This figure shows 2 normal distributions. The blue distribution has a mean of 50 and a standard deviation of 10. The red distribution has a mean of 60 and a standard deviation of 5. Both distributions are symmetric, with relatively more values at the center of the distribution and relatively few in its tails. This is the formula for the density of the normal distribution, which can be thought of as the height for a given value on the x-axis. The parameters u and sigma are the mean and standard deviation respectively, and define the normal distribution. The symbol e is the base of the natural logarithm, and pi is a constant. Since this is a non-mathematical treatment of statistics, don't worry if this expression confuses you. We will not be referring back to it in later sections. However, you will be using computer programs that make use of this formula implicitly.
Let me pause it right there. Specifically, what you're going to be using is either a table in your appendix that I'm going to show you after we finish watching our videos, and we're going to be using the graphing calculator, TI graphing calculator. You can use either one, which means you don't necessarily need a graphing calculator for this material. It just means if you don't have one, you're going to be using the table, all right?
Listed here are 3 of the 6 features of normal distributions that are going to be illustrated in the remaining sections of this chapter. Normal distributions are symmetric around their mean. The mean, median, and mode of a normal distribution are equal. The area under the normal curve is equal to 1.0. Normal distributions are denser in the center and less dense in the tails. Normal distributions are defined by 2 parameters, the mean and the standard deviation. 68% of the area of a normal distribution is within 1 standard deviation of the mean.
All right, so that's a pretty short video. None of these videos are terribly long. And next we're gonna look at the history of the normal distribution. It gets into previous material you look at, like histograms and probability. So when we're using the normal distribution, we're actually going to be working with probabilities, right? And as some of you may already know, the history of probability boils down to one thing: gambling. People who gambled wanted to know what were their odds of success, how much should they bet, and so on. And so they would go to mathematicians, and it sort of drove mathematicians to work in the area to develop the concepts of probability, all because people wanted to go to Vegas, or well, there was no Vegas back then. But anyway, you get the idea. All right, last video, and then we're going to look at a table.
In the chapter on probability, we saw that the binomial distribution can be used to solve problems, such as if a fair coin is flipped 100 times, what is the probability of getting 60 or more heads? The formula presented is the one you would use to determine the probability of exactly x heads out of n flips, where x is the number of heads, n is the number of flips, and pi is the probability of a head. In our problem, x is 60, n equals 100, and pi equals 0.5.
Now I'm going to pause it again. You guys have actually seen this formula back in chapter 5, and n is the number of trials, except in the formula in your textbook, they don't use x, they use r, the lowercase r. And over here where you see pi to the x power, they don't call the probability of success pi in your textbook, they call it a lowercase p, and the 1 minus pi they call q, right? So, but you've seen this formula, just not exactly with these letters or symbols.
Therefore, to solve this problem, you compute the probability of 60 heads, then the probability of 61 heads, 62 heads, etc., and add up all these probabilities. Imagine how long it must have taken to compute binomial probabilities before the advent of calculators and computers. Abram Demoivre, an 18th century statistician and consultant to gamblers, was often called upon to make these lengthy computations. Demoivre noted that when the number of events, or coin flips, increased, the shape of the binomial distribution approached a very smooth curve. Here is the binomial distribution for 2 events, for 4 events, and for 12 events. Notice how the distribution begins to form a smooth curve as the number of events increases. Demoivre reasoned that if he could find a mathematical expression for this curve, he would be able to solve problems, such as finding the probability of 60 or more heads out of 100 coin flips, much more easily. This is exactly what he did, and the curve he discovered is now called the normal curve. The importance of the normal curve stems primarily from the fact that the distribution of many natural phenomena are at least approximately normally distributed. One of the first applications of the normal distribution is to the analysis of errors in measurement made in astronomical observations, errors that occur because of imperfect instruments and imperfect observers. Galileo in the 17th century noted that these errors were symmetric, and that small errors occurred more frequently than large errors. This led to several hypothesized distributions of errors, but it was not until the early 19th century that it was discovered that these errors followed a normal distribution. Independently, the mathematicians Adrian in 1808 and Gauss in 1809 developed the formula for the normal distribution and showed that errors were fit well by this distribution. The same distribution had been discovered by Laplace in 1778 when he derived the extremely important central limit theorem. The central limit theorem is covered in detail in another section, but simply put, Laplace showed that even if a distribution is not normally distributed, the means of repeated samples from the distribution would be very nearly normal, and that the larger the sample size, the closer the distribution would be to a normal distribution. Most statistical procedures for testing differences between means assume normal distributions. Because the distribution of means is very close to normal, these tests work well, even if the distribution itself is only roughly normal. Quetelet was the first to apply the normal distribution to human characteristics. He noted that characteristics such as height, weight, and strength were normally distributed.
Okay. Now I'm going to get rid of that and share a different screen. And here's your different screen. So some of you have this, you might have gotten the formula card with your textbook. Some of you, well, if you have a hard copy of the textbook, if you open the inside cover, you'll see the table that we're going to use just right there when you flip open the book. So that's a shortcut way to get to it. And it's again in the appendix section, and it's on the card if you happen to have the formula card. So again, those of you that don't have a graphing calculator for chapter 6, there's going to be a table that you're going to use. And I'm going to show us how to use the table and how to do it on a graphing calculator. And when I can find an online calculator that'll do it, or if I can find a good one that you can do this on, I will let you guys know. I'll look at the ones that are already up because it might be on that. I haven't checked yet. All right, down we go. It's like A8. Here we go. A8 is the, I guess, the page number, you could call it, page letter number. So we're looking at table 4, areas of the standard normal distribution. Now, this is a standard normal distribution, all right? And we'll talk more about that starting next Friday. But all of these numbers that you see in the inside of the table, 0.003s and all of this kind of stuff down here in the center, those are actually probabilities. They're areas underneath of this curve. And what we're going to see is, as was talked about earlier, there was this really ungainly formula that you're going to see in your notes and you're going to see in your textbook, where they would have to go through and plug it in. It was that thing that involved E and pi, and raising something to raising it to a power and all that kind of stuff. And that had to be done like separately for each one of these little numbers. But if you standardize it, which we're going to learn how to do, you can use the table, which is nice. All right, so so if you look at this first table right here, the picture of it, you'll see the 0 is right in the center. That's the mean of the standard normal distribution is 0. And you'll see the z value is to the left of 0, right? And then you'll see this left tail area that's shaded in. So the inside of this table tells you what is the area of that blue, or how big is that blue area. And it corresponds to probabilities, like what's the probability that you're in that blue area right there, okay? And I'm going to go in and show you this, even though we'll talk about it more Friday. So for example, notice all of the z values going down this first z column are negative, right? Because the z is to the left of 0, we're looking at negative values. So the idea is, for example, if I go down to where z is -3, so let's say this is at -3 for this z value, and then I go up at the top, I go across to where it's 0.00. It takes it out to the hundredths place. Then this blue area we'd be looking at would be negative, where z is negative 3.00. What's the area to the left of it? Well, you would see where negative 3.0 meets 0.00, and it's 0.0013, right? Where does the row and the column meet? Right there. You're reading this sort of like that binomial distribution table, right? You go down and find your n values, and across the top you find your p's and where do they meet, that type of thing. Anyway, that's if you're working with negative z values. And then right after that, in your textbook, they give you the table if you're doing positive z values. Your z is to the right of 0. And remember, 0 is the mean, right? So what's the probability? And notice it's shaded to the left again, like the other one. So if you were right at 0, the mean, you go down to where z is 0.0, and then to the hundredths place 0. So the probability that it's to the left of 0 is 0.5. It's half of the curve, right? Which makes sense. It's like, imagine the z is actually on the 0 and all that left is blue, that type of deal. And we'll talk more about that again next Friday, but I wanted you to see these tables and how to use them. The central limit theorem, the last thing I want to talk about is that central limit theorem. So what we're going to end up doing is we're going to have normal distributions, right? Then we're going to run into sampling distributions, and we'll talk more about that. But it turns out that if you take samples of size 30 or more, the cutoff point is 30, and there's an extensive proof involving calculus that goes behind it, multiple pages. I had to study it when I was in college. If your sample size is 30 or more, what you can do is change the raw values to z values, and we'll take a look at how to do that, which would then allow you to use a z table, right? And that's, again, the central limit theorem that we'll talk about later. Any questions at this point? I know this is sort of just a rough, brief intro, but I didn't want to dive into actual calculations with this until after you've done your next test. So again, Wednesday's your test. Come Monday prepared with any final questions that you might have, all right? With that, if you have questions, feel free to hang around and ask. If not, have a good weekend and be safe out there. Almost there. Anybody else? Last time for questions.